So now we can talk about the max flow min-cut theorem. And using this theorem is actually very powerful when approaching maximum flow problems because it provides a different way of thinking about the problem. So the max flow min-cut theorem is applied in the following case. You are given a weighted directed graph and marked nodes S and T, and you call a subset of edges an ST cut if after all of those edges are removed, there no longer exists any path from S to T. The weight of this ST cut is the sum of the weights of all edges that you've removed. Your goal is to find the minimum weight ST cut, as in you want to remove the minimum sum weight of edges so that you can completely disconnect S from T. It turns out that, and this is proven with the max flow min-cut theorem, that the weight of the minimum ST cut is exactly equal to the maximum flow between S and T, when S is the source and T is the sink. When you put the weight or cost of removing each edge as the capacity of that edge in the flow graph. It is often easier to view arbitrary flow problems from this perspective of min-cut rather than viewing them from the perspective of max flow. And let's get into why this theorem might be true given intuition for why the min-cut is equal to the max flow. If we consider an arbitrary maximal set of edge disjoint paths that you would get when finding the maximum flow, we can see that at least one edge from each of these paths must be cut in order to fully disconnect S from T. And after cutting these edges on each of these paths, S and T must be disconnected, because if after cutting these edges S and T were not disconnected, that would imply some additional path is still connecting S and T, contradicting the fact that we have found the maximal set of edge disjoint paths. So we can kind of separately prove a lower bound and an upper bound and show that they must be exactly equal.